You've seen the renders, the sleek rocket noses, the Mars colonies, the bold typography promising humanity's multi-planetary future. And you believed it, or at least wanted to. The narrative is seductive. We are a species on the verge of breaking free, temporarily grounded by budget, cycles, and political will, not by anything fundamental. Elon Musk says we need to become interstellar. NASA agrees in principle. The implicit assumption underneath all of it is that distance is an engineering problem. Build a faster ship, find a better fuel, wait long enough. Get there. That assumption is wrong, not incomplete, not premature, wrong. We are not stalled. We are caged. And the bars of that cage are not made of money or ambition or political will. They are made of physics, of mathematics, of the cold, indifferent geometry of the universe itself. And once you understand the actual numbers, you will never look at a SpaceX launch the same way again. Let's start with Andromeda, not because it's the most distant object we can see, but because it's the nearest large galaxy to our own, our cosmic neighbor. On a clear autumn night in the northern hemisphere, you can see it with the naked eye as a faint smear of light near the constellation Perseus. It looks close enough to touch. It is 2.5 million light years away. That phrase rolls off the tongue too easily, so let's slow it down. Light is the fastest thing in the universe, not the fastest thing we've built. The fastest thing that can exist, according to every experiment ever conducted and every equation we have. It travels at 300,000 kilometers per second. To give that a human anchor, in the time it takes you to blink, light has circled the entire Earth 7.5 times. In 1 second, it reaches the moon in just over a second. It crosses the distance between Earth and the sun in 8 minutes. It is, by any reasonable definition, incomprehensibly fast. Now, send a beam of light toward Andromeda. Watch it travel at this unimaginable speed, crossing 300,000 kilometers every single second, for a year, then a decade, then a century. After 2.5 million years of continuous travel, it arrives. 2.5 million years. That is not a travel time. That is a geological epoch. When that photon left Andromeda to reach your eye tonight, our ancestors were not Homo sapiens. They were Homo habilis, chipping rocks in East Africa, with brains roughly half the size of yours, with no language, no fire, no concept of a future. That is the distance we are talking about, and that is the speed we would need to travel. And we cannot travel at that speed, not even close. Here is where the scale becomes genuinely disorienting. Voyager 1 is our most distant human-made object. Launched in 1977, it has been traveling through space for nearly 5 decades, and it is moving at approximately 61,000 kilometers per hour. By any terrestrial standard, that is extraordinary. It is roughly 50 times faster than a rifle bullet. It crossed the orbit of Neptune in 12 years. It has now left our solar system entirely, a staggering achievement of human engineering and patience. At that speed, Voyager 1 would reach Andromeda in approximately 44 billion years. The universe is 13.8 billion years old. Read that again. Voyager 1, our best, most audacious attempt at leaving our cosmic zip code, would need 3 full lifetimes of the universe to reach our nearest galactic neighbor. The stars that exist today will be long dead. New generations of stars will have lived and died. The solar system itself will likely have been absorbed when the Milky Way and Andromeda collide in about 4.5 billion years. And Voyager 1 still would not be there. This is not a problem of refinement. It is not a question of building a Voyager 2 that is twice as fast or 10 times as fast or 1,000 times as fast. Even if you increase Voyager's speed by a factor of 1 million, you would still be looking at a journey of 44 million years. And the mathematics do not bend to optimism. So the obvious response is, fine, we'll go faster. We'll approach the speed of light. Build a ship that can accelerate continuously. Given enough time and energy, get a spacecraft to, say, 90% of light speed. Then the trip only takes about 2.7 million years. Still impossible, but the direction seems right, doesn't it? Keep pushing, keep adding energy, and eventually, maybe we get there in a reasonable time. This is where physics plants its flag and refuses to move. Einstein's special relativity does not merely describe how fast things move. It describes the relationship between mass, energy, and velocity in a way that contains a fundamental, non-negotiable limit. As any object with mass accelerates, it requires more and more energy to continue accelerating, not linearly, not proportionally. The energy requirement rises toward infinity as velocity approaches the speed of light. Here is what that means in practice. To accelerate a hypothetical spacecraft with the mass of a large airliner to 50% of light speed requires roughly the same energy the sun outputs in several days. To get to 90% of light speed, the energy requirement climbs to something approximating the sun's total output over months. To reach 99%, you need exponentially more again. And to reach 100%, to actually arrive at light speed, you need infinite energy. Not a large amount, not a currently unavailable amount, an infinite amount. The universe does not contain infinite energy. Therefore, no object with mass will ever travel at light speed. This is not a technological gap. It is a mathematical proof. But suspend disbelief for a moment. Suppose some unimaginable propulsion system, some physics we do not yet know, gets a ship to 99% of light speed. Time dilation kicks in. From the perspective of the crew, the journey to Andromeda might subjectively compress to a few thousand years, which is still longer than recorded human history, but theoretically within the range of multi-generational ships. Fine, let's grant all of that. What happens when you arrive? Because the ship is moving at near light speed, time passes more slowly on board than it does in the rest of the universe. The crew ages less, but Earth does not. While the crew experiences their compressed journey, 2.5 million years pass on Earth. Every human being who exists today is gone. Every institution, every language, every city, every memory of the mission, gone. Whatever evolved from humanity, if anything did, would be as alien to us as we are to those Homo habilis rock chippers. Any signal sent back would take another 2.5 million years to arrive. The round-trip time for a single message is 5 million years. The ship would not be an explorer returning home. It would be an orphan arriving in a universe that has completely forgotten it ever left. Perhaps the engineers reach for the speculative tools, warp drives. The idea, proposed by physicist Miguel Alcubierre in 1994, is elegant in concept. Don't move the ship through space. Compress space in front of it and expand space behind it. So the destination comes to you. The ship sits in a warp bubble, technically stationary, while space-time itself does the traveling. The problem is not the concept. The concept is mathematically coherent. The problem is the requirements. The Alcubierre drive, as currently formulated, requires a form of matter with negative energy density, what physicists call exotic matter. This is not dark matter. It is not antimatter. It is a hypothetical category of matter that would need to have properties that violate everything observed in the universe to date. It has never been detected. There is no experimental evidence it exists. And even if it did exist, the energy budget for a functional warp drive, according to updated calculations, would need to exceed the equivalent mass energy of Jupiter. The entire planet Jupiter, converted entirely to usable energy for one trip. Wormholes present the same wall from a different angle. A traversable wormhole, a tunnel through space-time connecting two distant points, is permitted by the equations of general relativity. Einstein and Rosen described the mathematical possibility in 1935. But a wormhole, upon formation, is inherently catastrophically unstable. It collapses almost instantaneously. To hold it open long enough for even a single particle to pass through requires, again, exotic matter with negative energy density, the same matter that doesn't exist, the same equations that demand the impossible. And cryogenics, the idea of simply freezing a crew and letting time pass, runs into basic cellular biology. Ice crystals are not gentle. When water inside a cell freezes, it expands and forms sharp crystalline structures that puncture cell membranes, destroy organelles, and shred the molecular architecture that makes a cell functional. Suspended animation, as depicted in science fiction, requires halting every biochemical process simultaneously and restarting them in perfect synchrony. We cannot do this. We cannot do it with current technology, and the path toward doing it is not clearly visible, even in theory. There is one final dimension to this that most popular science misses, because it is perhaps the most unsettling. The universe is expanding, not just the objects in it, moving through space, but space itself, stretching in all directions simultaneously. For nearby objects, this is detectable but manageable. For objects beyond a certain threshold, roughly 14 billion light-years away, the expansion of space between us and them is occurring faster than the speed of light. Not because those objects are moving through space faster than light, which relativity prohibits, but because space itself is growing, and there's no law against space growing quickly. The result is a cosmic event horizon. Galaxies beyond that boundary are not merely far away. They are causally disconnected from us. No signal, no ship, no information of any kind can ever bridge that gap. They are not unreachable yet. They are unreachable. Full stop. Forever. The observable universe, which we tend to think of as enormously, generously large, is in fact the universe gradually sealing itself off. What we can see today represents more of the cosmos than we will be able to see in 5 billion years, because galaxies are crossing that horizon continuously, winking out from our accessible reality. The universe is not our oyster. It is contracting around us in the only sense that actually matters, the sense of reach. So here is where we actually are. We are on a planet orbiting an unremarkable star in one arm of a mid-sized galaxy. The nearest substantial landmass beyond our galaxy requires a journey that exceeds the current age of the universe by a factor of 3, even at speeds we cannot approach. The physics that would theoretically allow faster travel require energy inputs that do not exist, and materials that have never been observed. Time itself conspires against the traveler, and the universe is methodically, permanently placing its most distant regions beyond any conceivable reach. There is no maybe one day. There is no technology gap to close, no political will to summon, no breakthrough lurking just around the corner of the next century. The interstellar optimism that sells rockets and generates cinematic universes is, at the scale of galaxies, a profound and beautiful lie we tell ourselves because the truth is too structurally strange to sit with comfortably. We are, each civilization that exists anywhere in this cosmos, islands, separated not by ocean but by the physics of energy, mass, and the geometry of space-time. The distances are not challenges. They are walls built into the foundation of reality. And here is the thing about walls. When you finally accept that this one will not come down, not in a century, not in a millennium, not in a billion years, something shifts. The question stops being, how do we get out, and becomes, what does it mean that we're here? This planet, this specific unrepeatable arrangement of water and rock and oxygen and evolutionary accident, is not a launch pad. It is the destination. It is the entire point. Not because some force ordained it, but because the alternative, another version of this, another world where consciousness arose and looked up and wondered, is separated from us by distances that functionally do not differ from infinity. The fragility of this place, the thinness of the atmosphere, the narrowness of the temperature band that liquid water requires, the extraordinary improbability of the last 4 billion years of biology is not a problem to engineer around. It is the entire stakes of existence as we can actually experience it. We spend enormous energy imagining our escape. Perhaps the more honest, more difficult, more genuinely scientific response to the scale of the cosmos is to recognize what it is actually telling us. Not that we should explore, not that we should dream, but that what we have here on this specific rock, orbiting this specific star, in this specific and unrepeatable moment of biological and cosmological history, is the only version of this we will ever get. The universe is not indifferent to us. Indifference implies awareness. The universe simply is, vast and silent and governed by equations that contain no exceptions. And within that silence, something here learned to ask questions. Don't lose it.